All right, so these are those fundamental units again. In the U.S. Customer English system, the fundamental unit of mass is the slug. That's a cool unit. Completely pointless for us. We don't even care about it. We won't be dealing with it here. In dynamics, you might need to deal with it there, but for us, not so much. All right. So, but as a lot of things are given in kilograms, as the SI system shows, we'll be dealing with those. In force, in the English system, we have pounds, okay, and it's lb or the pound sign, or kips, kilopound. This is called a kip. We never call it a kilopound. It's always called a kip, but it actually is a kilopound because the U.S. customary system, the engineers were like, that SI system is kind of cool with the kilo, mega, milli, all that stuff, and they were like, maybe we can steal that and do better conversions. Because as some of you might know, a ton is 2,000 pounds. Man, that's almost a good conversion. Almost. Why they made it 2,000 and not 1,000 is beyond me. Kind of not the smartest because then you have to do the math, right? Kilopound or kip, the engineers invented and said, okay, we've fixed it. All right, so 1,000 pounds is a kip. So in statics, we don't care as much about time and mass. You'll get into those in dynamics and other courses. For us, pretty much force and length are going to be our main dimensions. Okay. In the English system, be ready to use pounds or kips, right? If you're in the SI, it needs to be in newtons. So if the problem is given with a weight that's in kilograms, immediately get that into newtons by multiplying it by 9.81 meters per second squared. All right. Last thoughts about the systems of units, since a lot of you are new to the English system, or at least new to it in science, meaning that you think that way, but you might not do math that way, or physics or statics in it. Let's talk about it a little bit. We're often talking about length as feet and inches. So I'm 6 feet, which is kind of boring. Let's say you're 6 feet 2 inches. You write that as 6 single tick mark hyphen 2 double tick mark. That is read as 6 feet 2 inches. The hyphen does not mean subtraction. For those of you logical people that use the SI system, that burns you up. I get it. It's not really the best. It's old school, right? It means you actually, that means you add the 2 inches to that number, but you can't add them directly because there are two different units. So if you wanted to put this into all inches, you could take 6 times 12 and get 72, plus 2 more is 74. So this is 74 inches. Or you could even say that if you put it into feet, you could take that 2 and divide it by 12, and you would get 6.17 feet. Okay. Anyway, the moral of the story is this is how it's going to be written a lot. So you need to be able to recognize that and understand. And now, pounds, okay? There are a couple ways to write the units. You can write it as LB, because LB stands for pounds, right? Of course not. That's dumb. It's from Latin. Libra, right? If you're into the zodiac, a goddess or whoever that had the scales. It's where she weighed decisions or weighed people's fates or something. I don't know. This is not a mythology class. This is statics class, but LB comes from that, so that's why it is that if you care. You'll see me write this a lot. What is that called? That's called the pound sign, right? Press pound for more options like your phone. Why do you think they call it pound? Because it is the unit, or a way of writing the unit pounds. So you can use that. I know, right? It's really cool. Never even thought about it. Pound sign, huh? All right, so you can just write, if it's 318 pounds, 318 pound sign after it. And it's really easy to write when you're writing by hand. The other good thing about it is if you write LB, like Libra here, like the written form of pound, if you're writing that by hand, that might actually look like 2 more decimals, like 1/6 if you're writing it by hand, which is kind of confusing. So that's another reason I like to write the pound sign. Keep in mind, they are exactly the same thing. They cancel out in the equations if you want or if you need to. So just keep that in mind. Pound sign. So just a few quick examples of conversions. You should know all this, but whatever. Let's convert 38 pounds into SI units. You would need to look up your conversion. This is in your exam reference sheet provided in this course, is where I got this one from, but there's countless other places you can get these conversions from. But there are 4.448 newtons in 1 pound. Remember, newtons and pounds are both force, right? Pounds are force and newtons are force. Kilograms, nah, they're not forces. They're not. They're mass. So don't make that mistake. Converting it into SI units, you want that in newtons. So you're going to take 38 pounds times 4.448, and you do it like this. So you can say, well, I've got pounds up here, so I need to have pounds down in the denominator. You know, it really comes down to, think about it. When you convert these things a lot, you're like, do I need to multiply by 4.448 or do I need to divide by 4.448? If you write this down like this, it becomes quite clear. You just need to have the stuff cancel. If the units cancel, give you what you want, then you know you did the math right. Amazing. 38 times 4.448 newtons gives you 169 newtons. Cool. Here's a good one. Convert 2 kips per square inch into SI units. So that's 2,000 PSI, to give the example of what we were talking about earlier with PSI. This is KSI, or kips per square inch. Okay. And so 2 kips per square inch is, you need to convert that into SI units. So we need to get rid of the kips and the inches and get it into things that they use, right? So using the exam reference sheet for this course, they don't talk about how to give you meters from inches. They do meters from feet, so I went ahead and showed it this way, although you could have that conversion factor too. They're, you know, on the internet or whatnot. But I went ahead and did it here longhand so you could see. So there are 12 inches in a foot, so that inch cancels with one of these 2 inches, because this is inches squared, right? So don't be that person that does, well, kips per square inch. If I want to convert inches squared into feet squared, I need to multiply by 12. No, you don't need to multiply by 12. You need to multiply by 12 squared, right? Because there's 12 by 12. So you have to do that conversion twice. And so now my inches cancel and I'm in kip per feet squared. Now I'm going to convert my feet into meters, and I need to convert this feet into meters and this one. These two both, so I have to do that conversion twice. And then I'm going to convert my kips into newtons. This one I did cheat a little bit because I only have on the exam reference sheet that 1 pound is equal to 4.448 newtons. But remember, a kip is 1,000 pounds, so that one's easy. So 1 kip is 4,448 newtons. And I get this enormous number here, 13,788,828 newtons per square meter, which is what a Pascal is. A Newton per square meter is a Pascal, so it's just that same number again in Pascals, which, you know, that's a lot of numbers, so we can use those prefixes and make it a little bit more simple, and also kind of reflect the right number of significant figures. This looks awfully exact. We really have no idea how exact that is. If you used a different conversion factor here that was off by just a little bit, this whole number would be quite a bit off. Okay? So just keep that in mind. So 13,788,828 would be 13.8 megapascals. Boom, done. All right. So units. You got to give me units because they're going to be different numbers based on which units you're using. You know, I walked 1 foot versus I walked 1 mile. It's a big difference. It's the same number. It's the same number. It shouldn't matter, right? Come on, he's being so picky. I didn't write my miles versus my feet. It makes a huge difference. Always write them. And if you show your units everywhere, if you're writing them and canceling them like I showed in the previous slides, it'll actually help you get the right number. You know, because if your units all cancel, most likely you got the right number. It might just be off with calculator error or something. But your chances of an error are greatly, greatly reduced if you write your units. Okay? And that's what I'm getting at here. Because most engineering equations, not all of them, but most, have dimensional homogeneity, which means the dimensions or units and all have to equate to each other on each side of the equation. All the terms have to have the same units, yada, yada, yada. Final thoughts here, okay? Statics is the mechanics of stationary and non-accelerating objects. So things moving at constant velocity and things that are not moving at all are all governed by the laws of statics. So that's actually a huge amount of engineering systems. Matter of fact, I'd say that's the majority of engineering systems. And even if it is accelerating slightly, if it's just slightly, maybe you can approximate it as being at rest or steady state. Myself being a structural engineer, a branch of civil, I do building design. We do that all the time with earthquakes, right? Earthquakes are a dynamic load. It's an acceleration. It's a ground acceleration. And what we usually do is think about the impact. We turn that into an equivalent lateral force, which is like an impact load, if you will, on the structure. And then we use statics because it's easier. So statics is easy, yes, but it's going to challenge many of you, most of you. Statics is a challenging course. And it's not because it's complex. It's actually simpler than all the physics and math that you just got through to get here. I think the reason it's challenging is because it's that first engineering course that you've taken. We're going to give you what I like to say is tools in a toolbox, and you're going to need to remember all of them and be able to grab them as needed to solve these problems. It takes practice. You can't just look at my examples on these slides and say, I've got that. You've got to get your hands dirty, right? You've got to try it some, because you'll start to see patterns. You'll start to see, like, oh, I see kind of how you approach this problem. Statics can be thought of as an art that uses physics to understand our world and design our future. That's kind of what I'm getting at, right? I mean, you have to say, I've got a bunch of basic little concepts here, all the forces. For instance, I can make an equation of equilibrium equal to 0. I can solve for all types of things that I didn't realize I could solve for before. Really extremely useful. Statics is super powerful, but you've got to just have the practice. So how best to learn it? Practice, 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 and maybe practice some more. Oh, and I forgot. Write your units and draw diagrams. Engineers usually think graphically. Draw something. I'm going to be asking you to draw lots of free body diagrams this semester. It is really what makes all this click. And I tell you, when I have a student come talk to me and say, I really don't get this, and I say, let me see your work, and they show me some work, usually 9.5 times out of 10, I say, oh, where are your diagrams? Oh, I didn't really have time to draw the diagrams. And, that's usually the problem. If you take the time to draw the pictures, to draw the diagrams, and to draw them right, you'll actually solve the problems faster. And more importantly, you'll solve them as opposed to getting them horribly, horribly wrong. So that's my little last bit of advice to you. Take the course seriously and think about it as tools in a toolbox. Draw the picture and say, how, with what I know, do I get the stuff I don't know? And complete your pictures.